A star that aged too fast. It should have burned steadily for billions of years, following a life cycle so well understood that astronomers can predict its future with confidence. Instead, this star appeared exhausted far too soon, displaying characteristics of age that should have taken immense stretches of cosmic time to develop. The star exhibited features that belonged to different evolutionary stages simultaneously, as if it had compressed eons into a fraction of the expected time frame. This was not a minor discrepancy, but a fundamental challenge to assumptions about how stars live and die. To understand why this star still unsettles scientists today, we need to revisit how stellar aging is understood. Stars live by predictable rules, governed by mass, composition, and energy balance, and their evolution unfold along timelines that rarely surprise. Modern astronomy relies on these timelines to measure the age of galaxies, trace cosmic history, and anchor our understanding of time itself. Stellar evolution models predict that a star of given mass will spend a specific duration on the main sequence, fusing hydrogen in its core, before progressing through subsequent phases of helium burning, expansion, and eventual death. These predictions have been validated across countless observations, making stellar aging one of astronomy's most reliable frameworks. That reliability is what made this observation so disturbing. When astronomers analyzed the star's light, they found signatures that did not belong together. Its temperature, brightness, and chemical makeup suggested conflicting stages of evolution, as though it had skipped entire chapters of its own life. According to established models, this combination should not exist in a single object. The spectral lines revealed heavy elements typically produced only in advanced fusion stages, yet the star's mass and luminosity suggested it should still be in an earlier phase. The contradictions were stark and reproducible. At first, the discrepancy was treated as error. Instruments were recalibrated, data was reprocessed, and alternative explanations were tested. Yet each revision reinforced the same conclusion. The star was behaving exactly as observed, even if theory insisted it should not. Multiple independent observations using different telescopes confirmed the measurements. The data was solid. The problem was that the data contradicted everything stellar physics predicted for an object of this type in this environment. As the evidence accumulated, a deeper concern emerged. If one star could appear prematurely aged, then the timelines used to measure the universe itself might be less secure than assumed. Stellar clocks underpin our understanding of cosmic history, and this star was quietly suggesting that those clocks might not always run at the same pace. Age estimates for star clusters, galaxies, and even the universe as a whole depend on reliable stellar evolution models. If those models could be significantly wrong in some cases, then the entire chronology of the cosmos might need revision. The stakes were not merely about one anomalous star, but about the integrity of cosmological dating methods. What made the moment profound was not the star's behavior alone, but what it implied. If stars can age faster than expected under certain conditions, then the story of the universe may be written with more variability than the clean sequences humanity has relied on for decades. The neat timelines and phase diagrams that filled textbooks might be oversimplifications, accurate for typical cases, but inadequate for capturing the full range of stellar behavior. This realization was both exciting and unsettling. Exciting because it suggested nature was more complex than models allowed. Unsettling because it undermined confidence in tools used throughout astrophysics. As researchers dug deeper into the data, the star's contradictions grew harder to dismiss, because every measurement reinforced the same unsettling conclusion. Spectral analysis revealed elements associated with advanced fusion processes, while other indicators pointed toward mass and temperature typical of much younger stars. The combination defied the orderly progression outlined in stellar evolution charts. Carbon, nitrogen, and oxygen abundances suggested extensive helium burning, yet the star's position on the Hertzsprung-Russell diagram placed it where younger, less evolved stars should reside. The stars seemed to exist in multiple evolutionary stages simultaneously. Attention quickly turned to environment. Astronomers examined whether external forces could accelerate aging, considering intense radiation fields, gravitational interactions with nearby objects, or past encounters that might have stripped material and altered internal dynamics. Each scenario offered partial explanations, yet none fully accounted for the star's apparent leap forward in time. Strong radiation could alter surface chemistry, but not core processes. Gravitational interactions could strip outer layers, but shouldn't change nuclear fusion rates. Mass transfer from a companion could add material, but the star appeared single. Every environmental explanation left questions unanswered. What complicated matters further was the star's isolation. It did not reside in a crowded cluster or an active region where extreme interactions were common. Instead, it occupied a relatively calm neighborhood, making its advanced state even more difficult to explain. There was no obvious catalyst for such rapid transformation. The star was not in a binary system where mass exchange could occur. It was not near a supernova remnant or active galactic nucleus where intense radiation might affect it. Its environment was ordinary, yet its evolution was extraordinary. This mismatch between setting and outcome deepened the puzzle. As models were adjusted to accommodate these observations, uncomfortable trade-offs emerged. Explaining the star's condition often required relaxing assumptions that had held true across countless other cases. Small tweaks solved this anomaly, but threatened to destabilize understanding elsewhere, forcing researchers to choose between preserving consistency or explaining the exception. Increasing assumed internal mixing rates could accelerate evolution, but would affect predictions for other stars. Adjusting nuclear reaction rates could match observations here, but would create discrepancies in stellar nucleosynthesis calculations. Every solution created new problems. The deeper the analysis went, the more the star became a symbol of uncertainty. It challenged the idea that stellar evolution follows a single, universal script, suggesting instead that multiple pathways might exist, shaped by subtle initial conditions that are easy to overlook. Perhaps stars with nearly identical masses and compositions could still follow divergent evolutionary tracks, depending on rotation rates, magnetic field configurations, or convection patterns established during formation. These factors were difficult to observe directly and often ignored in standard models, yet they might profoundly affect stellar lifetimes. In confronting that possibility, astronomers faced a difficult question: whether their models describe how stars always behave, or simply how they usually behave under familiar circumstances. The distinction was crucial. If models captured typical behavior but missed important variations, then they were valuable but incomplete. The question was whether the star represented a rare exception that could be safely ignored or an indication that the framework itself needed expansion. The conflict intensified as attempts to reconcile the star's behavior began to erode confidence in stellar aging as a reliable cosmic clock, because the anomaly could not be isolated without consequences. If this star had followed an accelerated path, then others might have as well, quietly skewing age estimates used to reconstruct the history of galaxies and the universe itself. Globular clusters dated by their stellar populations might be younger or older than calculated. Galactic merger timelines based on stellar ages might require revision. The cosmic distance ladder, which depends partially on stellar standard candles, might contain systematic errors. The implications cascaded through multiple fields of astronomy. Some researchers propose that the star's rapid aging was a result of internal processes triggered early in its formation, subtle differences in rotation, composition, or magnetic behavior that compounded over time. These factors were difficult to observe directly, yet they offer a way to explain how a star could exhaust itself faster without external disruption. Accepting this explanation meant admitting that initial conditions might matter far more than previously believed. If small variations during star formation could lead to dramatically different evolutionary timescales, then stellar ages carried larger uncertainties than typically acknowledged. This was an uncomfortable conclusion for a field that had grown confident in its chronological precision. Others argued for more dramatic scenarios, suggesting past mergers or mass transfer events that left few visible traces. Such interactions could dramatically alter a star's internal structure, effectively aging it prematurely while masking the evidence of trauma. The difficulty was proving that such an event had occurred when the environment offered no obvious clues. A collision between two stars or capture of significant mass from a passing object could leave a star with altered composition and structure. However, these events should be rare, and detecting their signatures after the fact was challenging. The hypothesis explained the observation, but was difficult to test. What made resolution elusive was how well established the existing framework was. Stellar evolution models have been tested against millions of stars, producing results accurate enough to guide entire fields of research. Challenging that framework based on a small number of anomalies felt risky, yet ignoring those anomalies felt equally irresponsible. The models worked spectacularly well for the vast majority of stars. They successfully predicted outcomes, explained observations, and enabled precise calculations. Abandoning or significantly revising them based on rare exceptions seemed precipitous. Yet science also demanded attention to discrepancies, especially when they were well documented and reproducible. As debate continued, the star became a point of tension between confidence and curiosity. It asked whether science should protect its most successful models from disruption, or allow rare exceptions to reshape understanding. In that tension lay the real conflict, not between data and theory, but between the comfort of certainty and the pursuit of completeness. Conservative instincts favored preserving tested frameworks. Progressive instincts favored expanding models to accommodate new observations. Both approaches had merit. The question was which served science better in this particular case. The climax of this story arrived with a reluctant shift in perspective, as astronomers accepted that stellar aging may not be governed by a single universal timeline, but by a spectrum of possibilities shaped by subtle and often invisible factors. The star had not broken the rules of physics. It had exposed how narrowly those rules had been applied. The realization was humbling. The models were not wrong, but incomplete. They captured dominant effects while missing secondary factors that could, under certain circumstances, become important. The star revealed that stellar evolution was more parameter-sensitive than previously appreciated. This realization led to a more flexible understanding of stellar life cycles. Models were expanded to allow for greater variation, acknowledging that stars with similar masses and compositions could still follow divergent paths depending on their early conditions and long-term interactions. The universe, it seemed, allowed for more individuality than the clean categories humans had imposed. New theoretical work explored how rotation, magnetic fields, internal mixing, and mass loss rates could alter evolutionary trajectories. Observational programs sought to identify additional fast-aging candidates to determine whether this star was truly unique or part of a small but significant population. The rigid timelines of traditional models gave way to probability distributions that reflected genuine uncertainty. The resolution did not undermine decades of research, but it reframed it. Stellar clocks remained useful, but no longer absolute. Age estimates gained error margins that reflected complexity rather than weakness, making cosmic history less tidy but more honest. The shift paralleled other scientific progressions where increased precision revealed previously hidden variability. Just as planetary orbits were more complex than perfect circles, and genetic expression more variable than simple Mendelian ratios, stellar evolution was more diverse than first appreciated. The science matured by acknowledging complexity rather than resisting it. Today, the star that aged too fast continues to be studied, not as a mistake to be corrected, but as a reminder that nature often resists simplification. Its legacy is not confusion, but depth, revealing that understanding grows not by enforcing uniformity, but by accommodating difference. The star serves as a case study in astronomical anomaly analysis, teaching students how rare events can inform theory even when they don't overturn it. It reminds researchers that models are tools, not laws, useful approximations that capture most behavior, but should not be mistaken for complete descriptions of reality. Sometimes the universe does not change its pace. It changes our expectations of how pace itself should be measured. The lesson extends beyond stellar evolution to scientific practice generally. Progress requires balancing confidence in proven frameworks with openness to their limitations. The best science holds its conclusions firmly enough to build upon them, while loosely enough to revise them when warranted. Sometimes the smallest shift in perspective becomes the beginning of a new future. And sometimes that shift is recognizing that exceptions are not failures to explain, but opportunities to understand more deeply. A star